Once again, thanks for your patience, everybody. My name is James Skelton. I am the Technical Evangelist in Machine Learning for Paperspace, and today I'm going to be hosting a tech talk talking about Stable Diffusion with Gradient Notebooks. I really appreciate everybody making the time to join us. We've got a really interesting talk, and by the end of this session, you should understand what Stable Diffusion is, how it, the original model Latent Diffusion, and also how to run and use Stable Diffusion within Gradient Notebooks. If you're not familiar with Paperspace or Gradient Notebooks, Gradient is a platform for building and scaling machine learning applications. You can explore a new library or data set in the notebook, automate pre-processing, training, or testing with a workflow, and bring your application to life with a deployment. I encourage you to join our community of over 500,000 users on Gradient and get in on these awesome free GPUs and really, really cool technology. Okay, before we jump into the presentation, we're going to be having a presentation and a code demo today. Before we go into the presentation, I would like everybody to follow along with me to create our notebook so that you can all actually do the Stable Diffusion generation yourself. So what we do is log into console.paperspace.com, and if you don't already have an account, you can make one. It's free. You only need a free account to participate. Then we're going to navigate to a team or project of our choice. As you can see, I was having some issues a moment ago. And then hit the Create Notebook button in that top right of the project page to get here to the notebook creation page. Then select this icon with the dog, Stable Diffusion. Then, and you're not going to see this on my screen, there should be an option for a free GPU. If it is unavailable, that may be due to the 80 or 90 of you that are all participating right now. I suggest you just check back in again later today. I will be sending the instructions and everything out to you in this call. They're in the slides, so you'll be able to do this on your own. Once you've clicked Stable Diffusion and the free GPU, or a more powerful one if you so choose, hit Start Notebook. Then that will begin spinning up your machine, and I already have one ready for me here. There are a few steps we need to walk through that would be better for everybody to do right now at the beginning of this session, so I'm going to show that. So what you're going to want to do is go into huggingface.co. If you don't already have an account, you're going to need to create one. Again, it's free. And then if you click on the link in the notebook, right here where it says huggingface.co Compass Stable Diffusion V-14. You can't see it on mine because I've already done this. Actually, let's see. Let's do a private window. Here we go. You can see that there is a ask to get the model repository access. You must click that if you want to use the methodology I'm using today. Then once you've clicked on that, you will have full access, and all you need to do is go into your settings and then click on access tokens and copy your access token. I'm going to be deleting mine after this call, so do not worry about seeing mine because I'm going to show it in a second. And then here, you're going to want to unhash this line to get the login.py file from GitHub. Then we're going to use this function to quickly log ourselves in, and that will give us access to the model. Once that is done, we're going to make an outputs directory to put our images in. And then my suggestion is just to go ahead and run this now. This is the first one. This first cell works on free GPUs. Worth mentioning, it may give you an out-of-memory error first. If that happens, just restart your kernel and do it again. It will work after a try. But it just takes a second to download, so I wanted to make sure that we did that before we jumped into the presentation. And I see that somebody's been raising their hand several times. If you have something to ask, please, let me see. Oh yeah, you asked about the recording. I'm sorry, you must have missed it a moment ago. The recording will be available after this call. I will be emailing it to everybody and posting it on YouTube. If you have another question, feel free to add it in there. Oh, the chat is indeed disabled. I was unable to re-enable it. I see that you're still raising your hand. I'm not seeing a different question from you other than the one. So if you have a question, please feel free to throw it into the questions. Okay. Let's get back into my slides, and I'm going to go ahead and send this link out to all of you so that you can follow along and do the steps that I just described a moment ago. Oh, I just realized this is probably not available. Let's do this. Okay. So if everybody clicks on, I'm so sorry. I realize now that I did not send out the slides, so please excuse me. Follow the same instructions that are written here on the third slide. They're the same as I just said, other than the actual ones we did in the notebook with getting the Hugging Face stuff, but those are also described in the notebook. So if you missed what I was talking about, or you don't remember because it was a lot of steps, which is completely reasonable, there are instructions for you. The one thing to note is you're going to want to select a free GPU if it's available. If there is not a free GPU available, it will be later today. There's just about 100 people in here, and that is probably cutting into the availability. It will be available later today, though. So just check back in and follow these same instructions, and you should be good to go. One moment, please, while I just out. Just making sure I didn't miss any questions. Don't seem to have. Okay, and just remember, everybody, if you have a question, just throw it into the Q&A. I'm sorry, the chat was disabled for some reason. I'm not sure why. Okay. Without further ado, oh, you know, actually, I haven't gotten a response in a moment. Can I just get a like a lowercase b in the chat from, or in the Q&A from people that they've gotten all the instructions and the links and that we are good to proceed? Okay. Thanks, Rafael. Hi, Tom, Matthias, and Ali, and Yves. All right, we are sorted then. Okay. Let's get through this theory, and then we can start generating some fun images. Okay, somebody was unable to copy it from the chat. Okay, I can type an answer to that. Okay, you should have been able to see the answer to your question, the person that was unable to copy the link from the chat, and that will have the link in it. If you are seeing that there are no free GPUs, I'm so sorry. You're just going to have to check back in later today. The availability does go quickly when we have so many people participating at once. Okay. So here's a quick overview about what we're going to cover in the slides. First, we're going to cover just some general introduction to image generative network frameworks. So just kind of an introduction to image synthesis and some of the most popular paradigms for doing so. Then we're going to introduce diffusion models and the concept behind diffusion. Then we'll jump into latent diffusion models, which are the underlying framework upon which the pre-trained Stable Diffusion model was built. We will break down its architecture and in detail before jumping into talking about Stable Diffusion, the training data that was used, and talking about image synthesis with Stable Diffusion. We'll also briefly talk about some of the uses of the model and a comparison with competitors before going into our code demo. And at the bottom here, I've got 4 images that I made using the exact same steps we're going to follow today. With my prompt, a rabbit walking on a steel beam over New York City in an old vintage photo with grainy film. And I'm kind of happy how it turned out. It almost looks like one of those construction photos from the 20s. Okay. Image generation from, oh. So sorry, everybody. I am having a small technical problem. Shoot. How can I mitigate this quickly? 2 seconds, everyone. My monitor has just shut off. Put that back in. Hopefully that will turn on. Okay. And one moment, please. Don't freeze on me. Okay. Sorry about that, everyone. Oh, Keith wants to have more time spent on the material and not the administrative content. Well, thank you. I will do that right now, Keith. I appreciate your input. All right. So, image generation, an introduction to image generation frameworks. Image generation is the process of generating new images from an existing data set using machine learning or deep learning. This can be either supervised or unsupervised. Unsupervised image generation involves generating images without user-guided direction and reduced bias. And supervised image generation uses various forms of conditional guidance like text prompts or classification to guide the process to some target image or feature set. Over on the left, I have some examples produced from, I believe, Google's Imagen, judging by the picture in the top left corner, showing off some creative possible uses of an robust image generation framework. I particularly like the very cute panda rolling dough. Next. Arguably, the 2 most popular modern methods for this in deep learning are based on generative adversarial networks, or GANs, or diffusion. GANs start with a pure noise input and an image. Through iterative comparisons of the noised image with the original input by a discriminator, the model learns over time how to recreate the features of the image with the generator, sorry, typo, with the goal of eventually fooling the discriminator with the generated images. StyleGAN, for example, is famous for creating realistic faces for people that don't exist. Diffusion models use a process to learn how to recreate image features via the re-addition of noise to a noisy image, called denoising. Unlike GANs, they start with real image data only, and a popular example of this would be the ablated diffusion model. That's just one that exists outside of our talk today. So let's jump into what you all came here for in more detail. Diffusion models are iterative models that take random noise as inputs. Well, a random noise image, or sorry, they take an image that and then takes in, Diffusion models are iterative models that take in an image with random noise as inputs. This can be conditioned with a text or an image so that it is not completely random, and it iteratively learns to remove this noise by learning what parameters the model should apply to the noise to end up with a reapproximation of our inputted image source. Because the model has access to the real images during training, it is able to learn the ideal parameters and features through this application of noise. These noise images are similar, being of noise from largely the same distribution. By reverse feeding similar noise back through the model, we can expect to return an image similar to the ones we used during training. So as we can see here on the bottom, we are starting with some input, adding noise, and this noise makes it into a better, prettier looking version of the input. This is just one of the potential uses of diffusion with an initial image as opposed to a text guided input that we are going to be mostly using today in our demo. So latent diffusion models. In latent diffusion models, a compressed image representation is used instead of the image itself, and then that is worked to reconstruct the image in the diffusion process. Just like the clip model that I'm sure many of you are familiar with, the encoded inputs do not have to be restricted to one object type and can be a mix of text and visual data that is kind of merged together through attention. This allows for textual and image encodings to be encoded in the same subspace. And it also allows for textual influence of the generation process through prompting or possibly images or other things like that. This is made possible because the latent diffusion model has access to those real images during training and is able to learn the right parameters. Sorry. Once it is applied the noise to the image iteratively until it's reached its completely noise state and is unrecognizable, then we can re-noise the image until we get back to our desired reapproximation of the output, with all of the noise being that similar in general distribution we talked about a moment ago. Since they are encoding the inputs, you can feed it in any kind of input like images or text, and the model will learn to encode these inputs in that same subspace. So it's really just a more advanced version of the same diffusion process I described in the slide before. Oh, I'm sorry. I'm getting word that there is a mic issue. Can everybody hear me okay? Can I get a follow-up? If there's a problem, I can fix it. Okay, seems like it's mostly fine. Yeah, everybody, bombard me in the chat, in the Q&A. If there's ever a problem, I will fix it. But it looks like we are good. Okay. Yes, so it's just a it's basically it's applying a similar process as the general diffusion with that compressed image representation that makes it so much more efficient. Let's look at how it does that and talk about the architecture. So looking at this more closely, we can see that we start with some initial image X. And then we encode it into an information dense space called the latent space, or Z. Now that we are in the latent space with our condensed input, we can then do the same thing with our conditioning inputs, which are either text or images or anything else. And that's this X, I forget my notation, but X with a tilde over it. And then merge them with the current image representation using attention. The attention mechanism will learn the best way to combine the input and conditioning inputs in this latent space. These merged inputs will then act as our initial noise for the diffusion process. So we get our attention to combine that factor here. And then the diffusion process is just kind of the same as we've been using. It takes that initial image, noises it, and then adds more noise to get the image to reapproximate the initial input. It also uses the conditioned or the text conditional inputs that we merged to, or image conditional inputs, but the additional inputs that we merged for the conditional generation to affect the overall output from the original input. Taking this modified and denoised input in the latent space, we are able to reconstruct the features of the final image from coarse to fine. And moreover, these feature representations and other new ones can be adjusted, transformed, and displaced with the guidance of the prompt. This is how we are able to actually get latent diffusion models and now stable diffusion in our example to generate images that are impossible to find in any real world data and are really sometimes impossible to even imagine with our human brain. So in this next slide, this is from the Latent Diffusion Models GitHub. Here is an example showing the image-to-image in-painting and upscaling functions of the latent diffusion models. This is in-painting right now. Now upscaling and image-to-image. So image-to-image is able to take this kind of basic picture and then turn it into something much more detailed. In-painting uses masking to create changes to specific areas in an image, and upscaling raises the quality of the image. So all of this and a bit more, stable diffusion and latent diffusion models are capable of. So it's a really, really powerful tool for a variety of different applications and tasks. All right, let's talk about stable diffusion. So it can be argued that this is the follow-up work to latent diffusion models. It is the release of the pre-trained versions of latent diffusion models from the researchers at CompVis, who are the original creators of latent diffusion models. So I just had a question I wanted to make sure I got. This is not recovering data, but creating new information in an image. I may need some clarification from you, William. Sorry about that. I'll answer it as soon as you clarify. These Stable Diffusion was initially released to the public on August 22nd. Okay. I'm still not sure what you mean by that, Aleem. I understand it's not recovering data, but creating new information and image. Oh yeah, I guess that's what in-painting. Yeah. They're all created. They're using the information from those images to infer and predict what data would be there in place of it, and following the prompting that we give it. So in the case of in-painting, we're telling it to make it look like that object that we've masked isn't there, so it masks over it. It's creating new information. It doesn't know. Sorry. Okay, let's really focus on Stable Diffusion now. So as I said, it was initially released on August 22nd to the public. It is currently on its 4th iteration, SDV14. To go into a little bit of detail about this, the pre-trained models were initially trained on the Leon 5 billion dataset subset, Leon high resolution, which consists of 170 million examples from the Leon 5B dataset with resolution of 1024 by 1024. The subsequent models were all trained on a different subset of Leon called Leon Aesthetics v2.5, which all have an estimated aesthetic score, which is basically their own computer. I'm sorry, I saw the question, lost track of what I was saying. Their own deep learning model for assessing the aesthetic appealing beauty of an image. So how well it aesthetically is pleasing, or it fits some beauty metric. It's basically a way of saying these images are not too ugly to use, or too grainy, to whatever it may be that make them unfit for an image dataset training. A question. Anybody can ask comments, or questions using the Q&A, and everybody will receive a recording of this. It'll also be on YouTube. in addition to that aesthetic score, they were also filtered to the original size, 512 by 512 images, and an estimated watermark probability of less than 0.5. You will see this sometimes where a random watermark looking gibberish of letters comes up. They did their best to get rid of that, but it's still somewhat present. Let's talk a little bit more about this training data. Leon's image data sets are built off of Common Crawl, which is a nonprofit that scrapes billions of web pages monthly and releases them as massive data sets. Leon collected all HTML image tag pairs that had alt text attributes and classified the resulting 5 billion pairs based on their language to filter the results into separate data sets using their, as we mentioned a moment ago, resolution, predicted likelihood of having a watermark, and aesthetic score, which they described as subjective visual quality. The data itself is around 48% from the same 100 sites, including around 7% or just under 7% from Pinterest. User-generated data made up the majority of these, so the data set is actually pretty varied and robust to a lot of different contexts, including stuff like different artist styles, celebrities, figures, politicians, things like that, and even creating new artwork of fictional characters. All together, the choices they made for the training, starting with the high resolution and then working down to these aesthetically pleasing and without watermark images, allowed a really high level of quality and robustness to be given to the pre-trained model, and a massive advantage compared to a lot of other, I'm guessing, future pre-trained versions of latent diffusion models in understanding really varied and nuanced subject matters. Stable diffusion is really strong at handling very long and complicated prompts with lots of different descriptive elements. Got a question. Do they train the model in NVIDIA's DGX station? Because there is a lot of data. I'm actually not sure. I can't recall what they trained it on. I only remember that it was very expensive. If it fits in your training set and output. Okay, I had a question about the difference between training set and output between DALL-E, Midjourney, and Stable Diffusion. I would need to look directly at those. One thing I can speak to right now. No, I'm sorry. I'm not confident in my answer, so I can't speak to that directly. At the end of this session, we can talk about those. Okay. So using Stable Diffusion for image synthesis. Come inference time, the training data makes Stable Diffusion probably the most general and powerful image synthesis model ever released to the public. And that means it's the most powerful one that you can use in about 5 minutes from now. Stable Diffusion text to image is capable of creating any number of creations at the behest and prompting of the user. These are highly influenceable and complex, detailed and nuanced, and still able to be remarkably accurate to recreations to those prompts. That being said, it is not perfect. AI cannot understand everything about language. Let's use my example prompt I have here. If you remember earlier, I had a pretty complex prompt about a rabbit crossing across New York City, I guess an iron beam over New York City. I can't remember the exact prompt. This one is arguably a bit more complicated, but I wouldn't say much more so. A human man in a black tuxedo suit walks on the surface of the moon, eating ice cream and holding hands with a Cookie Monster. Painting by DALL-E, high detail, 4K, 8K. So what I've done is I've got a relatively not complex series of actions between this human man and the Cookie Monster, and I've given it in a way that I think would be very interpretable to a human. I've also told it to be in high detail and to approximate a image in the style of the painter DALL-E. what is going on here is trying to combine all these different, so disparate features into one has confused it, and it's just really not sure how to make the thing that most closely approximates our prompt. So many different things could approximate our prompt uh, in a way better than this that it could randomly produce. So it tries its best to get as close as possible. And a good way you can influence this is with something called the seed, and I'll show that when we get into the code demo. You can change the seed at any time in your image generation process, and that will affect, well, it allows you to get a degree of control over the randomness. So we can control the prompt directly, which controls what our influencing conditional data is, but the seed, if I remember correctly, is essentially a value that it uses to base the randomness off. So if we alter the seed in any way, a difference, I mean, a seed of 1 and a seed of 2 will give you completely different traits if you were to look at thousands and thousands of generated images on the same prompt across different seeds. Okay, let's continue. In addition to text to image, the current version of Stable Diffusion also supports image to image synthesis as well. This is where it uses an initial image as a baseline rather than pure noise, and can allow for clever modifications to existing images. Future releases will add capabilities for upscaling and inpainting, and those are indeed available for latent diffusion models, but there isn't a diffuser's built-in way, basically. So it will require a little bit of engineering to make it work. But in theory, anything that is working with the existing latent diffusion model, of which there is its own repo with its own scripts, should work with Stable Diffusion, as it's just a pre-trained version of Stable Diffusion. Okay. Next. All right, the last thing we're going to talk about before we go into the code demo, now that we understand kind of what Stable Diffusion is and what it can do, let's talk about how it compares with some other models. As you can see from the tables above, LDM, which is Stable Diffusion, consistently outperformed competing model frameworks for unconditional and text conditional image synthesis on a variety of tasks and data sets. Projected GAN, seems to be the only consistent model that can outperform Stable Diffusion for unconditional synthesis, and really just for scenes. I take that back. Scenes, and yeah, it consistently, latent diffusion models were able to do well on celebrities, but projected GAN doesn't work with rooms, so it wouldn't be able to do that anyway. It's a scene model. So other than something that is particularly optimized for creating scenes, Stable Diffusion is fantastic, and it's a really, really excellent choice. For conditional or text conditional, I should say, synthesis, Make a Scene does outperform it in general. Take that with a grain of salt, because it outperforms it in this FID metric, but there is no use of their IS metrics. So there's a direct comparison cannot be totally made, but it seems pretty clear that Make a Scene is going to do a little bit better than LDM in terms of your generated images proximity to the initial inputs, which is what FID measures. I have to actually look up what it stands for, but FID is a measurement of the fidelity of your image generation. Here we go. It stands for Freshet Inception Distance, and it uses to assess the quality of images created by a generative model. That IS stands for Inception Score, which I mentioned earlier. So it looks like there isn't an Inception Score for Glide and Make a Scene. So take these with a grain of salt, but FID is considered the de facto metric. So I would consider make a scene superior still for text conditional synthesis. Based on this, though, I think it's pretty safe to infer that Stable Diffusion thrives when dealing with objects and entities, more so than a background scene. This is likely due to the extremely high variation in the training data and the lack of a focus on background scenes. In a lot of these images, I'm sure there are people standing with things in the background without any attention given to those backgrounds, and those essentially become confounding noise to the model come training time. But we can't have a perfect world where every image is perfectly captioned and described, especially because we don't know exactly how that is yet. But I would say you should consider using Stable Diffusion for any tasks that involve people, animals, smaller scene settings, and other entities of that ilk. Cartoons, artwork, things of that variety. Stable Diffusion will do really well. It does seem like you may be better for specifically scenes and rooms to use another model like Projected GAN or Make a Scene. Next. Across all competition for class conditional ImageNet latent diffusion models with recent state-of-the-art methods for class conditional image generation on ImageNet, we can see that LDM4 consistently in terms of FID and inception score and precision were the best performant model. This shows that just generally across, if you need a model for a general kind of text conditional, image conditional, whatever it be, task, it is a good idea to use Stable Diffusion. It will do really well in comparison to the competition. On other tasks, such as in painting, this continues to be conserved and largely the case as well. I did not show it here, but it is also the case for upscaling tasks. We can see that the LDM4 had the highest FID score on these 40 to 50% mass samples and across all samples, and nearly the same level of LPIP score as Lama, which is considered one of the premier models for in painting. I would argue, therefore, that latent diffusion models and, by extension, Stable Diffusion is a viable and powerful tool to use across image synthesis procedures of any type, in particular in painting, upscaling, and conditional image synthesis when using human, animal, biological entities, small objects, and basically anything outside of landscapes and rooms, but it'll still do a fantastic job with those. Okay. So here is basically a similar slide to what we had at the beginning. Or it's a lot of the same information that we had at the beginning. To access Stable Diffusion, all you need to do is click on this link, which I showed earlier, and click the acceptance to the agreement. Then you will need to log into Hugging Face and get your access token, but it is hosted for free on Hugging Face. All they ask is that you accept their license agreement, not to abuse the model that they're giving out for all of us. So please make sure that you do that and use your best judgment on ethics for using Stable Diffusion. The model can be used on any GPU-powered machine via Python scripting or in a notebook. I recommend a more powerful GPU for this for sure. The free GPU will do it, but you can get a lot faster on just about any A series or V series machine, and it really flies. It's really impressive when it gets going. Okay. So I'm not going to walk through how to do this again. If you missed how to do the code demo, you can either click this link or follow the instructions below. And you should be able to get into your notebook. Then there are instructions inside the notebook that will show you how to run all the code and make the best use of everything. I've also provided some resources that I recommend everybody check out. In particular, I want to give a credit to Louis Bouchard. He's a wonderful blogger in the deep learning world. His breakdown of latent diffusion models is really insightful, and I definitely recommend everybody check that out. Okay. Let's get back into our notebook. And if you weren't here at the beginning, I'll just very quickly run through this. You're going to want to run this first cell to install all the necessary imports, and then follow the instructions here. You may need to unhash this one line and paste your token when you get it here. This will log you in and make sure that the access that you just gave yourself by agreeing to the Stable Diffusion guidelines is actually usable and that you can pull from Hugging Face. Then you will want to make sure that you create this outputs directory, which I could not see because I hadn't refreshed that. And just because it will try to save to that, and it will cause an error if it is not available to save there. So I've produced 5 images, just real simple, of a Corgi astronaut on Mars. This first cell, by the way, is the free GPU cell. And what we're doing here is we are loading in some variables, our model ID, which Hugging Face is basically the Hugging Face repo, you can think of it as. Our device is CUDA, since we are going to be using a GPU. Then there is this pipe function that I want to call some attention to. This from pre-trained method, I mean. It takes in our model ID and our auth token, which we have added in to get the model from Hugging Face. And it's good to notice this bit right here. This is what tells the model to load in FP16. We're going to want to use mixed precision, this lower precision training in order to run on the free GPU. This will not cause any significant loss in the quality of the images outputted. I've tested it significantly myself. It's essentially the same. So there's virtually no loss in using FP16, even if you were on a more powerful GPU. Next, we are, oh, so sorry, I had a request to zoom in. Is that better? Ah, cool, thank you. Yeah, so this torch D-type and revision are where you get the FP16. That's very important. I had somebody ask if there's going to be a recording. There will be a recording on YouTube and emailed to all of you. Yeah, torch D-type, FP16. This is how you get your model loaded in half precision. Then we are going to use .2 to make sure that our pipeline uses the GPU. I'm going to finish this and then answer questions at the end, just to make sure that everybody knows how to run this. I'm sorry. I just want to make sure that we get through the code demo, and then I will stay on to answer questions as long as needed. We are using that .2 to make sure that the GPU and CUDA are being used. Then we are defining our sample number. This is just going to be the number of samples we are creating. You can change it to be as much as you want. Then I'm going to create an empty list to dump these into. Then when we call the pipeline, it takes in our prompt, which is a Corgi astronaut on Mars. Then the guidance scale. This is our these classifier free guidance, and basically it modifies how intensely and how close, or intently and how closely and meticulously the model will try to follow your prompt. So I read in a Reddit guide, you can think of 1 to 4 as being like, go nuts model, make whatever you want to an extent. Then around 5 to 7 is, okay, I want to influence this a bit. 7 to about 8.5 or so is I want a lot of control. I want this to be very similar to my prompt. And then as you approach 9.99, it tries its best to approximate that as closely as possible using the text encodings to match to the image feature encodings. Next, we have our height and width. This is actually the default values. I don't recommend you ever change these. You can make it run on 256, but the model was trained largely on 1024 and 512 size images. So as a result, it doesn't know really what to do in such a low definition context, and it tends to make things look kind of like fried, I suppose. Like if any of you are familiar with the term, like a fried meme, where it's lost a lot of its quality and it's grainy and there's odd warm colors all over the place. It doesn't work in 256 by 256. So keep that in mind. The number of inference steps. This is I would say the second most important after the prompt. This is what determines how many DDIM inference steps the diffusion model is taking, or how many steps it's taking to add and denoise, or how many steps it's taking to denoise from the noisy original to get to our approximation of the prompt with the image features. You are going to get diminishing returns after 50 in my experience. It will stop you after 500. 500 will take a really long time. 50 takes, I don't know, about, what's it say, 5 seconds, 2 seconds on the free GPU. So pretty fast. My recommendation is to stick between 50 and 100 and produce bulk images by changing the sample num until you get something closer to what you want. You're going to want to go with the quantity, not quality, most likely, in terms of how you're going, or quantity of images more so than quality of your prompt in trying to get it to approximate your desired output. Yeah, if you produce a significant number of images, the likelihood of one that is closer to what you want will be possible. Next, seed. I described this earlier, but it basically is a value which can affect the randomness of our model. So if we want it to have consistent randomness, you would keep the seed the same. I have it defaulting to random currently. This is at your discretion. I've also got this scheduler, LMS discrete scheduler. I just thought it worked better, so I added it in. One final one that may be worth mentioning is you can change the sampling. I have found PLMS to be quite good. And you can find more details about what those are in the GitHub repository and the actual text-to-image.py script, which is therein. Okay, so and then finally, I'm iterating through again and saving those. I likely could have just put those in the same loop, but I didn't. In this next cell below it, we have the high cost version of this for FP32. You can just ignore this for now. Basically, all that's changed is that it doesn't have that use FP16 argument in the from pre-trained method. One thing you can also do, this is kind of purely optional, is I've adapted Boris Dema's clip re-ranking. What this will do is it will assess your images based on the accuracy to the prompts as determined by the clip model. We can then rank our images by this output to find what is kind of, if not objectively, computationally the most accurate prompt. So here is, or image to the prompt, I should say. So finally, here is our ranked examples. Got, this looks more like in space than on Mars to me. That's pretty cartoony, but pretty accurate. So I'm guessing that's why it got a lower score than this one, which is a little less cartoony. And there's some artifacting going on this one's head and mouth. I'm guessing that was a big problem. This one looks like an emoji, which is thoroughly amusing. And this one looks like a toy keychain or something made out of plastic. That's fantastic. And finally, one thing you're absolutely going to want to do, especially if you are trying to create pictures of anything with people in it, animals, things like that, is use GFPGAN. The GFPGAN package comes fused with another release from Tencent Art called Real ESRGAN. These are really the best upscaling and facial restoration models that you can use with any image generation paradigm. I definitely recommend, if you are going to ever use some image you generate from Stable Diffusion for something professionally, that you run it through this first. All you need to do that is just run this cell, which will install the packages and get the pre-trained model for you. And then this will generate our upscaled and facial restored images. Just take a moment. In the meantime, I will get into questions. Once it's done and everything's upscaled, that is the full walkthrough. I definitely encourage you all to play around with this. My favorite prompt forever and always will be Chris Pratt starring, or I guess it should be dressed as Super Mario. If you're not familiar, he is playing Super Mario in the Super Mario film, and that is just endlessly funny. Okay, so it looks like GFPGAN is going to take a second to download. It's just about 2 minutes, so you're already seeing what we're getting there. It's just going to look a little bit bigger and sharper, so we're not missing out on anything. But I encourage you to all check that out. I see that we're at the hour. If anybody has any questions, please feel free to throw them in the chat right now. I'm going to reshare the link to the slides if anybody was unable to see it. Here are the link to the slides. I can also, let's see. Yeah. Okay, I'll open the floor to questions, but I just want to really quickly say before everybody leaves, thank you so much for attending. This is a great session. Sorry for that hiccup at the beginning. Once we got through that, had a lot of good information to cover and some really, really cool image synthesis modeling to show off. I definitely encourage all of you to play around with this on your own time. If you do not have access to the notebook right now because of the free GPU availability, check back right after, about an hour after this call. I guarantee that at least with today, by the end of the day, there will be availability. It usually evens out after the workday. But it's a really powerful model that you can use for just about everything in image generation. If not at the best level, then very close. Yeah, thank you all so much for attending, and I really hope you have a wonderful rest of your day.